Assalamu alaikum. This video I am going to record to demonstrate the hardware in the loop implementation of robust active fault tolerant controller that I have designed to control my quadcopter in the presence of actuator faults. This is my hardware setup. You can see that my FPGA board is connected with my laptop, and this file is just for the sake of simulation based file. And in this file, this active fault tolerant controller block is representing my robust active fault tolerant controller, and this is my second file where this FIL block is representing an FPGA which is connected with my laptop. So now you can see that the LEDs on the FPGA blocks are blinking, which indicate that FPGA is not yet programmed. Now I'm going to upload my bitstream file into the FPGA board. Bitstream file for the active fault tolerant controller. This is my bitstream file for active fault tolerant controller. Now I have started uploading the bitstream file into my FPGA board. The file is being loaded. You will observe that once the file is loaded, LEDs will stop blinking. So LEDs has stopped blinking, and I also have obtained the message that FPGA programming file loaded successfully. It means that now my robust active fault tolerant controller has been uploaded on to the FPGA board. Now I can perform hardware in the loop simulation. So now this setup is representing my hardware in the loop implementation setup. Here I can apply the motor number, and this is my fault vector. And here in this condition, let's try, for example, motor 1. It means that I have set the fault on motor 1, and my fault vector is 0.1 and from 0.1 to 0.5, and the timing of the fault are given as 15 from 15 second to 95 second. It means that I am applying the 10% fault on motor 1 at the time of 15 second. Then I am applying the 20% fault on motor 1 at the time of 35 second, and so on. I am applying the fault of 50% on motor 1 at the time of 95 second. So now I'm going to run my hardware in the loop setup. Now my hardware in the loop setup is in working condition. You can see that now my controller is running on FPGA board, while my quadcopter model and the trajectory planner and the simulation actuator files are modeled in the Simulink environment, while my controller is running on FPGA board. Now the hardware in the loop implementation is in action now. So my hardware in the loop implementation is completed. Now we can see the results. These are the trajectories, desired trajectories, and the reference trajectories. From the graphs you can observe that the desired trajectories and the actual trajectories are approximately same. It means that the quadcopter trajectories are following the desired trajectories. Similarly, if I want to see the speed of each motor, You can see that these are the graphs for the speed. In this simulation I have applied the fault on motor 1. It means that as the magnitude of the fault is increasing, the speed of the motor 1 is supposed to be decreased, and from the graphs we can see that the speed of the motor 1 is decreasing. As the fault value is increasing, the speed is decreasing. And similarly, the speed of the other motors will increase to compensate for the loss of effectiveness of motor 1. From the graphs we can see this very clearly. From these graphs we can easily observe that as the fault on the motor 1 is injected and the magnitude of the fault is increasing, the speed of the motor 1 is decreasing, while the speed of the other remaining three motors is increasing to compensate for the loss of effectiveness of motor 1. Similarly, we can now just modify from here. For example, if I type 2, similarly I can now simulate or perform hardware in the loop implementation for faults on motor 2. Then again all of these graphs will be plotted in the same way. And again then I can re-enter the motor number as motor 3 or motor 4 to inject the faults on any of the motors of the quadcopter to verify that my robust active fault tolerant controller is in working condition on actual FPGA board. That's all from my side. Thank you.